Summer is here in Mumbai and it's hot and I'm not running the AC. There's a nice breeze, but if I open the window there's a very large hissing sound in the recording, so I'm going to do it with a sweaty face, so pardon me for that. But this is a nice paper that's looking at the risk of hydrogen economy for atmospheric methane. Hydrogen is all the rage in terms of clean fuels for the future, and the various ways in which hydrogen can be produced in larger and larger scales with lesser and lesser greenhouse gas emissions is being discussed all the time. Newer and newer approaches are being innovated, as we discussed with direct hydrogen production from seawater, for example, from MIT. And obviously they can have all sorts of co-productions and reduce greenhouse gases, but there is the danger of hydrogen itself leaking out because it's a very light gas, hard to track its leakage and the sinks and sources. So we have to be aware of how much hydrogen is leaking out and how it's interacting with the methane that's there and will be produced from fossil fuel emissions and other natural sources along the way. So let's first look at the color spectrum of hydrogen, which you have probably heard of. I have already discussed it elsewhere in other podcasts, but I wanted to put in here since it's still relevant for this idea of discussing what the dangers of a hydrogen economy are for increasing or decreasing atmospheric methane, which is 26 times the greenhouse warming potential compared to CO2, which we have to worry about. Production of hydrogen can occur via the use of electricity or fossil fuels, which gives it the colors, and the technology and feedstock and greenhouse gas footprints are qualitatively discussed here. So obviously electrolysis is always the biggest or the most preferred method of producing hydrogen, since there is water, especially so much ocean water. Right now lots of fresh water is being used, and this is raising flags about how that will compute with fresh water security, etc. already. So looking at green hydrogen, the feedstock would be electricity used in feedstock would be wind, solar, hydro, geothermal, and tidal. So obviously these are renewable energies, and that's why it's called green. And the greenhouse gas footprint should be minimal, but that's not very comforting unless we can quantify it with a life cycle analysis and so on. Purple and pink hydrogen have nuclear as the source of energy, again with minimal emissions. Yellow hydrogen has mixed origin grid energy, so it's still electricity, but its footprint is listed as medium. Blue hydrogen has natural gas reforming plus CCUS gasification plus CCUS, and uses natural gas and coal as feedstocks, and has expected low greenhouse gas footprint. Turquoise hydrogen uses pyrolysis, very high temperature chemical reaction, so obviously you can expect that it will be burning things like natural gas to extract hydrogen, but it will have solid carbon as a byproduct, which would be easier to deal with. Or if you use gray hydrogen with natural gas reforming, with natural gas being the feedstock and the energy source, then you have medium footprint. Brown and black hydrogen use gasification and use brown coal like lignite or black coal as a source of energy and feedstock, and will have high greenhouse gas footprint. So that's really worrisome in terms of tracking the impact on methane, but also on greenhouse gas emissions. If you just look at summary of hydrogen projects in the GEO database, this is from Global Energy Infrastructure. You can see that of the total energy production, gray hydrogen is right now at 49%, with 89% of the facilities operating and producing these. 14% of the total projects are for blue hydrogen, of which 50% are operating as of 2021. I should mention that when this report came out. Green hydrogen is 25% of the total projects, with 18% only operating as of 2021 when this report came out. Coming back to the paper on hydrogen impact on methane, hydrogen is expected to play a crucial role in reducing greenhouse gas emissions. However, hydrogen losses to the atmospheric chemistry, including positive feedback on methane, the second most important greenhouse gas. Here we investigate through a minimalistic model the response of atmospheric methane to fossil fuel displacement by hydrogen. We find that methane concentration may increase or decrease depending on the amount of hydrogen lost to the atmosphere and the methane emissions associated with the hydrogen production itself. Green hydrogen can mitigate atmospheric methane if hydrogen losses throughout the value chain are below 9 plus minus 3%. Blue H2 can reduce methane emissions only if methane losses are below 1%. This is a tall order for methane, for containing hydrogen. We address and discuss the main uncertainties in our results and the implications for decarbonization of the energy sector. It's a nice paper, but I'm not going to go into all the details of the implications they are talking about. Let's just define critical hydrogen emissions intensity for methane mitigation first. The quantification of the critical hydrogen emission intensity, HEI critical for methane mitigation, is key to assess whether displacing fossil fuels with hydrogen would mitigate or enhance the tropospheric burden of methane. Here we investigate how the HEI critical is affected by the hydrogen production pathway and by two of the most uncertain terms in the methane hydrogen OH balance. OH radical, very tiny percentage in the atmosphere, very hard to track, short lifetime, highly reactive, and so on, a precursor to many other chemistry reactions in the atmosphere. The first one is partitioning of the OH sink among the tropospheric gases. Secondly, the rate of H2 uptake by soil bacteria. The derivation of an analytic solution for the HEI critical is reported in the methods. The methods also lists a lot of the chemical reactions that are involved in the model in calculating these H2 CH4 OH reactions and interactions, which I'm not going to show here. But let's look at the tangled hydrogen and methane budget. Sketch of H2 and CH4 tropospheric budgets and their interconnections. Firstly here, composition for the competition for OH. So you are looking at reaction with OH of methane and hydrogen. This requires 518 is the number, so that are the sources there for various numbers used here. So the range is 474 to 532, and 19 is the concentration or the flux for hydrogen with a range of 15 to 19. This has a range of 474 to 532. So this feeds the H2 production for methane from methane oxidation. Methane oxidation at 23 teragrams per year of flux. So on the other hand, volatile organic oxidation will give you 18 teragrams per year. They have both ranges. The range for VOC is 10 to 18. For methane oxidation is 15 to 26. Okay. Concentrations in the atmosphere for H2 is at 530 parts per billion. Methane is 1890 parts per billion. Anthropogenic increases are noted very clearly since the beginning of the Industrial Revolution, but methane is not well mixed like CO2. It doesn't last as long. Its residence time is only about a decade, and it has ups and downs which are not always very easily explained in terms of the causes. OH on the other hand is only 63 parts per quadrillion, so 10 to the minus 15. So that's a tiny amount there. In terms of the hydrogen economy, you are looking at the ranges of methane and hydrogen at 0 to 370 and 0 to 230 teragrams per year. And from fossil fuels, you are looking at 111 and 11 respectively. Other emissions, 465 and 24. And the soil uptake for hydrogen is at 60 and methane is at 38 teragrams per year in terms of the fluxes. Okay, the flux estimates come from some references provided in the paper you can look up. The potential emissions minimum maximum due to a more hydrogen based energy system. Flux estimates arrows scaled with the mass flux intensity, so you can see the changes here. Thickness is related to the mass flux intensity, so 518 versus 19, 23 versus 18, and the range is here. Okay, on per mole basis, H2 consumes only about 3 times less OH than methane. ppq is parts per quadrillion, as I said. top-down estimate, including also minor atmospheric sinks, which are less than 10%, are included. So those are the A and B that are listed here, which I didn't talk much about. So in B, the range is obtained as a difference between total and fossil fuel emissions, which is here for methane. Okay, so the hydrogen replacement of fossil fuels is envisioned this way for H2 replacement of fossil fuels in percentages, and the change in hydrogen sources in teragrams per year for the various scenarios going from 0% to 1 to 5 to 10%, and here you're approaching higher and higher hydrogen emissions intensities as you do that. And if you look at change in sources for methane in teragrams per year, depending on the methods used, the scenarios are 2% blue H2, these are leakages 1% and 0.2%, and for green hydrogen you can see the sources are negative, so you would expect reductions in methane with H2 replacement of fossil fuels in terms of percentages. Okay, so changes in H2 sources delta SH2 as a function of fossil fuel replacement for different hydrogen emission intensities shown here. In B, changes of methane sources as a function of fossil fuel replacement for different H2 production pathways. Methane leak rates associated with blue H2 production are 0.2, 1 and 2%, which are shown here. Bands of delta SCH4 account for different amounts of blue H2 produced and lost. Okay. In C, we are looking at response of the tropospheric concentrations of H2 and methane for the emission scenario of the previous panels here. Symbols mark the different percentages of fossil fuel displacements. So here is the delta CH4 in parts per billion versus delta CH2 in delta H2 in parts per billion, and you are looking at percentages in terms of replacement of fossil fuels. Okay, only symbols for 100% fossil fuel replacement are reported for blue H2 with 1% CH4 leakage. So they have to assume for the model how the H2 is produced and how much leakage happens in terms of methane from the production itself. Also reported is the difference in CO2 concentrations delta CO2 equivalent that would produce equivalent radiative forcing to the change in equilibrium methane here in the upper axis. Okay, so you have to track all these things, but you get the idea that the green and blue hydrogens, so green hydrogens here on the negative side of delta CH4 in terms of compared to fossil fuel emissions, and also in terms of delta CO2 equivalent in parts per million here. Okay, both are negative on this side, and the blue hydrogen based on various ranges of replacement, you have various levels of delta CO2 and delta CH4. Obviously I'm being very brief, but you get the idea that when we are going to move towards replacing fossil fuels with H2, we have to worry very much about how the H2 is produced and how much of the fossil fuel is being replaced and how the methane leakage and the H2 emissions intensities themselves are controlled along the way. If you look at the methane response to increasing H2 production, changes in H2 and CH4 sources delta S shown here due to green and blue hydrogen of around 500 teragrams per year. HEI is the H2 emissions intensity, as we said. Gray lines mark the case for HEI is 0% here, which doesn't appear here, for example. Blue bars are for delta CH4 are obtained for HEI is 10%. Okay, so you can see the various numbers. Response of CH4 methane concentration. The right axis shows the delta CO2 equivalent here. That would produce equivalent radiative forcing to the change in equilibrium methane. So methane is a non-CO2 greenhouse gas, as in the previous figure. We have to convert it to CO2 equivalent using its greenhouse warming potential, which is 26 times the CO2. You have to also use the time of forcing, like 100 years or so, for both to compute the equivalence. Nonetheless, delta S for methane for green hydrogen is negative, for blue hydrogen is negative if you keep the leakages low, and it goes positive when you reach 2% of the leakage. Okay, as before, we have to track the leakage. These are scenarios, but once you know these numbers, you have to ensure that the leakage remains below that, right? So for H2, they are all positive in terms of delta S. So as you produce more and more H2, you're going to add more and more H2 to the atmosphere. Delta CH4 versus hydrogen emissions intensity. Obviously, as hydrogen emissions intensity increases, you head towards positive numbers in terms of delta CH4, which is what we want to avoid, and that would increase delta CO2 equivalent in terms of ppm as well for radiative forcing, which is what causes the greenhouse gases. So obviously, keeping the emissions intensity low is very critical to reduce atmospheric methane concentration increases. In fact, to keep it to a decrease, you have to have emissions intensities of less than 9% plus minus 3% for green hydrogen, and you can see green hydrogen jumps to positive here if you go beyond that. And if you use blue hydrogen, then it has to be less than 1%. If you reach 10% HEI, you're going to have fairly significant increase in methane as well as its radiative forcing. Looking at critical hydrogen emissions intensity for methane mitigation, so critical HEI in percentage for green and blue hydrogen with various percentages of methane leakage. Critical hydrogen emissions intensity for methane mitigation, critical HEI as a function of OH excess, EOH shown here on the horizontal axis, and hydrogen production method, green and blue, H2 with 0.2, 0.51% CH4 leaks respectively. Dashed dotted lines are obtained for a 20% increase or decrease in H2 uptake rate by soil bacteria. Triangles mark the critical HEI for the best estimate of excess OH. So various parameters represented here. Soil uptake of H2 is something that they are tracking in the model, and of course there are all sorts of uncertainties associated with those, because with temperature increase into the future, with various changes in human activities on agriculture, land use, soil moisture, precipitation distributions, and so on, these numbers can have fairly significant uncertainties, so you should track those. So obviously, again, re-emphasizing that as the OH excess increases, you can allow higher critical HEI because you have reactions that will create the interactions between methane, hydrogen, and OH that we talked about before. Okay, so to read a few messages at the end: to maximize the climate benefit of hydrogen adoption, minimizing both H2 and methane losses across the supply chain of hydrogen production will need to be a priority. On the methane side, some governments and companies have already committed to reducing the leaks from the oil and gas sector, because this could be the most cost-effective and impactful action for near-term climate mitigation. New agreement was made on reducing methane emissions, I think by 50% by 2030, which is very critical considering the dangers of methane as a greenhouse gas. The International Energy Agency estimates that with the recent rise in natural gas prices, the abatement of methane emissions from the global gas and oil sector could be implemented at no net cost. So gas prices are bringing in more income, so you can drive methane emission capping with no net cost. Hence, the accomplishment of this mitigation is only a matter of political will for the limited number of companies involved. Well, that good-heartedness has to play out. Our versatile atmospheric model allowed a broad exploration of scenarios in a hydrogen-based energy system. The simulations with high-resolution three-dimensional atmospheric chemistry models, which are more comprehensive but more computationally demanding, could refine our results for specific scenarios. In particular, a more detailed model could improve the assessment of H2 displacement of fossil fuels by accounting for the emission changes of other chemical species like carbon monoxide and NOx, which impact the methane, hydrogen, OH dynamics. Atmospheric chemistry is very complicated, so future global warming will depend very critically on these. Further analysis could also refine the potential changes in emission inventories due to H2 displacement of different fossil fuels. Coal has to go, so it depends on each particular fossil fuel and how H2 displacement will affect emission inventories. So just a brief introduction. Please go ahead and read the paper and the enormous number of references involved in there for the details, and the method section which explains the model and the various chemical reactions and the assumptions that go into making these scenarios and so on. Okay, so I'm going to leave it here for now.